Too many stars, too little time. A couple years ago, in April 2018, the MIT-led NASA mission TESS launched on a SpaceX Falcon 9 rocket out of Cape Canaveral. It was a spectacular launch. And TESS is a mission that is looking for planets around other stars. Here's an image taken by TESS. This actually is just a tiny fraction of what TESS sees. TESS is essentially 4 glorified telephoto lenses. They're only about 10 centimeters in diameter, but they have a giant baffle to block out stray light. And these 4 cameras are wide field, and they're all bolted together. They're all bolted on a platform on a spacecraft in a big orbit around Earth. And they stare at one patch of the sky for a month, a giant strip of the sky. I'm one of the leaders of the TESS mission, and we actually meet every Tuesday and Thursday to find planets, actually. Our computers look at all this data, look at millions of stars, and flag planets, and we search through them. Here's how TESS finds planets. You can see the planet going in front of the star. We don't see that. That's an artist's conception. We see what you're seeing on the graph, where a planet goes in front of, we measure the brightness of stars, millions of stars, as a function of time. And we see a tiny drop in brightness that may be due to a planet. And when this planet finishes going in front of the star, the light curve or the brightness of the star returns to normal. And each time the planet orbits the star, that same drop in brightness will happen over and over again. And actually, thousands of planets around other stars, called exoplanets, have been found this way. And we meet like every Tuesday and Thursday to review planet candidates that have come from our computer searching the brightnesses of millions of stars. And there's kind of a long story about the field. It's quite mature now. It's even somewhat tedious. That's hopefully not being recorded. But we find these planets all the time. There's thousands of them. So 20 years earlier, I was a postdoc at an iconic, idyllic place called the Institute for Advanced Study. It's not at Princeton University. It's in Princeton, about a mile away. Back in those days, we didn't have thousands of planets, about 30 planets. And I put this chart for you, showing you the number of planets as a function of year. So you can see on the far right now, there's lots of planets, hundreds of them. But earlier on, when this takes place, there's about 30 or 40. And there's no planets that go in front of the star. Actually, for a planet to go in front of the star, as seen from our telescopes, the orbit has to be very specially aligned, like literally just edge on. So we only see some small fraction of them. One had been found, but not by but it had been already a known planet that people had followed up and seen to transit. There's a lot of ways to find planets listed there in colors. You don't have to worry about those, but the transit technique that we use with TESS that's so standard today, it wasn't in use then. When I was at Princeton, when I was at the Institute for Advanced Study, I met Gabriella, also a postdoc. She was a postdoc at Princeton, and it was just so fun. We met, we just really hit it off. She was just so funny. She was so brilliant at math, and it was like the first time I had a best friend in science. Now, what was great about Gabriella was, in addition to being a postdoc at Princeton, she had an affiliation in Chile. And in Chile, there are telescopes on the mountains because it's so dry. And the air is clear, and you can do great astronomy. But each country that owns a telescope there, they give 10 to 15% of their telescope time to Chileans. So she counted as a Chilean. So together, we sat down and figured out what could we do to apply for this telescope time. And we decided we would search for planets by the transit technique, which wasn't a thing then. There were less than 5 groups working on it. But it was still a competition, and we were postdocs. It wasn't our specialty or anything. So we proposed to use this telescope in Chile. It was a 4-meter telescope, wide field of view, and we were successful. And Gabriella was an observer, and she was really great at math and algorithms. I was good with strategy, and I worked on exoplanets. I won't say I was, or maybe I should say am, or I was great at programming. So she would like dictate algorithms, and I would literally just program them. And we worked so hard. We were working like nonstop. I literally could program without making a mistake in those days. Yeah. So we worked a lot on this project. And so other people were working on it too. It was amazing. It's like the going to the North Pole. It's like exploring. Like there was this wide open field ahead of us, so many stars, so many planets. Someone was going to be the first one to find it, and we wanted it to be us. It was way ambitious for 2 postdocs. We actually added some more people to the team later. We'd tell people about the project, and they would say, well, who's the PI? It's like, I'm the PI and Gabriella. And they'd be, no, like, who's in charge? It's like, no, we are. OK, so here's a small, tiny area of the star field. It's just for show. Our field was very wide. We had lots and lots of stars. It was 1,400 times bigger than this. It's just to show you some stars and what they were like. We worked hard. We were having a great time. Like we would work, and then she'd come to see my family. Like she'd hang out with me at my apartment, with my dog. We'd take my dog for a walk. We'd go out for lunch. We'd go out for dinner. We were just working nonstop, trying to get this job done. Let's see. There's like okay. So here's some data. Each one of these is a target star. So I'm just showing you 3 stars out of tens of thousands of stars. On the y-axis, it's showing you brightness. The stars, don't worry about the unit. It's this arcane kind of astronomy unit. And on the bottom, it's time in days. So each one of these rows is 1 night, essentially 10 hours. And so it's like reading a book almost, like read from the bottom up to the top. We had 11 nights. One's missing because it was raining. It's not supposed to rain there, actually, but we wanted a lot of telescope time. And they gave us time in Chilean winter, which is when it rains, actually. It rains there. It's bad for astronomy. And some of the data is crummy because it was cloudy or the air was messy. And so on the left here, you can see it's a variable star. It's a star that's changing in brightness on and off, on and off, on and off. It's called a Delta Scuti star, and there's lots of stars out there. They're just varying. In the middle, you see a drop in brightness, like the cartoon thing I showed you. It turns out that one is too deep and it lasts too long to be a planet. It's some kind of binary star. This next one, we actually thought that we found the first planet ever by this new method. And we were really excited about this planet. We told the other members of our team. We started up writing our paper. That would go in Nature, of course. And we actually had some other telescope time to follow up this planet, because this is just showing you a little drop in brightness, but it turns out lots of things can cause a drop in brightness. 2 stars, there's other kinds of false positives. And we had to get time on a bigger telescope using a different technique that, make a long story short, we just needed it to follow up and get a planet mass and figure out what it was. So we got the time, and it was Q observing, so the data came to us. Gabriella analyzed the data. We knew what we should see with this other technique. A planet's a planet, and some stuff were known by then. It was supposed to show almost like a sinusoidal variation that matched the period of this object. And what did Gabriella see? Absolutely nothing in the data. It turned out that what had happened was we had discovered this false positive. We hadn't found a planet. We'd found a false positive. It's called a blend. And what happened was we had seen, presumably, a star, like instead of a planet orbiting a star orbiting, transiting a star. And that would have a giant drop in brightness, so huge. But there was another star, like on the same pixel. It must have been like a triple star system. And that other star shown here was throwing light into the transit signal, making it super shallow. This is extremely common now. Back then, we didn't know. We thought we had a planet. We spent all this telescope time following it up. This is extremely common. No problem, back to work. Back to working nearly around the clock and not doing anything else on the project. So one day, Gabriella came into work inconsolable. I couldn't get anything out of her. She was incredibly upset. But she'd come to tell me something. It's did someone die? I mean, I don't know what this was. And eventually, she was able to kind of spill it out that all that summer, and this was towards the end of the summer, we were rushing to get our work done, she had been talking to a famous old male astronomer at Princeton. And he had been asking her almost on a daily basis about the project, technical details, really nitty-gritties. She had just found out he was working on the same project. Different mountain, also in Chile, different telescope. And honestly, if he's such a super famous astronomer, why did he need to do this? He didn't, right? He could have figured this out with his team. Well, Gabriella went into a mental dive and never really recovered enthusiasm for the project. They didn't have mind heart and all that back then. But the problem was my bad. I didn't have the skill to pick up her part of the project. And so it just kind of languished. When you make an experiment, because before that I had just been a programmer, like a modeler, so at least I got to understand data. That's what my postdoc advisor said. But if you do an experiment, it's like a layer cake. Every layer needs to be just right, perfect. We had a problem because one of our layers was bad. And that was our telescope was so big, 4 meters. We had to look at very, very faint stars. They were really too faint to do the kind of follow-up work that we needed. Remember I told you TESS has these 10 centimeter? I'm talking about 4 meter. Well, that was too bad because we couldn't really, it was a big, kind of a mistake looking back. But this other professor's team, meanwhile, they were also looking at really faint stars, and they put out 20 planet candidates, and a different team followed them up to get the mass and see what they were, and later on that same year, someone else found the first planet by the transit technique. Like, I'd invested a lot in this, and it was my best friend who, at the time, was kind of in the process of losing. I was just crushed, and I mean, I don't seem that upset about now because it's a long time ago. I was just so crushed, and I remember I went to a conference out in Seattle, and with a really good friend went on a hike on Vancouver Island, and I saw a bald eagle fly low across the river, and I just thought, you know, the world is still a beautiful place. So one thing, that blended object I told you about, that false positive, we noticed that the transit light curve was really suspicious. Like, when a planet transits a star, it crosses the limb of the star and the light just drops. It's like a box. But this wasn't. It was very, very slanted. And so Gabrielle and I started working out the equations that describe a light curve, looking at them more closely. It was just algebra. We were writing on like blank paper. We were in her small office. There was paper everywhere. We went out for lunch, and then we went for dinner. It was nearing midnight. It struck midnight, and we just started seeing something really familiar in all this crazy algebra. And at the very same moment, we both looked at each other, burst into laughter, and said, density. We had discovered that the light curve of the star, the light curve from the planet transit, it can actually tell you about the density of the star. Now, I don't have time to explain why, but I know most of you would understand it if I had time. But we actually know the density of stars because of the star type, the type of stars. There's like a grid library that you can associate it with, and you know the mass and size, therefore the density. So if the density from the light curve does not absolutely match the density of the star just from regular, what you know about stars regularly, then there's no possible way that that light curve can be due to a transiting planet. So we had discovered that the precise shape of the transit can tell you whether it's a blended false positive or not. So I kind of realized this is the only thing I'm going to get out of the project, despite all those years of working. So I worked really hard. We worked really hard. We got our paper out. And even though it's not my favorite paper, I'm still proud to tell you that this paper gets cited a few dozen times per year and has hundreds and hundreds and hundreds of citation. It was a paper I wrote at the beginning of my career, but it still has really stood the test of time. Now, I actually know there's a planet in that data somewhere. I'm convinced just because of the numbers. And I still do feel sad about it, actually. And all the things that went wrong, like, I still carry those with me today, and they guide my decisions in how I go about my work and choose my projects today. Thank you.